Okay. Thank you, Leo, for putting pressure on all of my data. So, I've gotten the opportunity to talk about how we can combine readily available data to be able to understand pandemics. And first, I'll just make a quick note. Okay. Quick note about myself, of course. First, I'm a bachelor student of the Cognitive Science program at Aarhus University. On my day-to-day, I work as an assistant data scientist at Innova. And I primarily study or use machine learning and data scientific methods such as natural language processing to understand societies and people in societies. So, the thing I'll talk about today, and the buzzword of the day, as we like to use a buzzword, of course, is social compliance and how social compliance affects COVID-19 incidents. I'll talk about what social compliance is or how we define it later. And of course, I've written it with my two colleagues, or my two friends, Thomas Lykke and Palle Willesen. So, social compliance is, by our definition, the interaction between social mobility and government restrictions. So do you follow the government's restrictions when they tell you to do something like staying at home? So this general prevalence to follow societal restrictions. Yeah. Our starting point of this problem or this paper was the literature that you see here. The fact that warmer temperatures reduce the prevalence of viruses, that mobility trends have an impact on the transmission. And we heard Laura earlier on the online transmission that lowered mobility is associated with less traveling time and fewer COVID-19 cases. Yeah. So how do we advance this evidence? We have all of this readily available data. We're students, so we can't really go out and make an intervention study. But we can use the things we have at home. And thanks to SSI, and thanks to Google, and thanks to a lot of people, we wanted to understand this reaction from the population and how they reacted to government implementations and restrictions throughout the time of the past 1.5 years. Further, we wanted to understand how weather affects COVID-19 incidents during different periods of stringency. So first, question or wonder, which is also directly related to Leo's point. What's the biggest problem we face when using observational data compared to an intervention study? This will be very relevant when we go into this weekend to work with data. The answer is very short, which can be said in many different ways, but my answer is omitted variable bias. We have a lot of things in our error term that we are not necessarily interested in studying. So we get this collider bias, as Leo talked about. Yes. But we made a model. So I've named this a pandemic and autoregressive process. And what is an autoregressive process? It's a process where the y variable in a, for example, a linear model depends on itself or on its previous values in the past. So you can predict the process by its own lagged values later. So this is the first thing that we added to our model. We have COVID-19 incidents as the dependent variable and COVID-19 incidents lagged as the independent variables. And we started our period of analysis from the 1st of September, and that was primarily due to people not getting tested over the summer. So we had a very bad sample of the population during the summer, but we expected that people would start to get tested more in September, or we could see that from the tests. Yeah, we define incidents as the above. So we have this panel data set up because we used cases in every municipality. So we have every of the 98 municipalities cases or positive cases. And we did this so we could implement a mixed effects model with random intercepts to reduce municipality incidence variation and to reduce daily incidence variation. Yeah. So you see the full model up in the right corner. We have incidence lagged, we have stringency in the model, we have weather variables, We have mobility data, we have municipality demographics, and we have interactions. And I won't have time to go into all of this, so we'll focus primarily on mobility data and weather variables. But first, I need to introduce how we measured stringency. So stringency we took from Oxford University, and they made this composite measure of government stringency based on 9 different variables in society. So we took this time series and added it to the time series from the SSI, and we had a national average of the stringency index for every day. So that's the next thing we add to our model, just like we followed the DAG throughout the talk. The next thing we add is weather variables. We took this directly from DMI, or not directly, a lot of pre-processing and painful hours. But we know that weather affects social mobility. We know that virus is less, or virus loses stability in higher temperature and is less prevalence. So that's why we introduced those. We introduced 2. We primarily thought that temperature would affect COVID-19 incidence, both because of social mobility and because of virus prevalence, but we also added precipitation. Yeah. Next up, the next thing to add to the model is these reports from Google Mobility. And these were made to study COVID-19. So Google gave this opportunity to be able to get an average change in mobility in these 6 categories. So it's a measure of how the number of visitors in a given place changes through, compared to some baseline that was set in February 2020. We focused on residential areas and transit stations, and this was primarily due to the bias that could come up when using retailers, because retailers has been closed a lot. Grocery stores has been open the whole time. So we would have this bias in the timeline if we added all of them. And we primarily just wanted to see, do people stay at home when they're supposed to? So returning to our hypothesis, as I've written, how has stringency and mobility change affected COVID-19 incidence? So we introduce residential mobility change and transit mobility change, the 2 in the bottom corner, to the model, and defining social compliance. So social compliance is when the stringency level is high and residential mobility is high, we assume that social compliance is high. People are doing what they're supposed to do, they're staying at home. I know that this can vary in any way, and there can be a lot of bias with this, but it's what we get when we use observational data. Yeah, so the next thing we wanted to look at, or how do we look at this? So we look at the interaction between mobility changes and stringency. We add an interaction between residential mobility and the stringency index, and we see how this affects COVID-19 incidence in the present. And remember the time dependency. So it's mobility changes and stringency and its interaction 9 days ago. Yeah. The point I'm trying to make here is that we added these interactions for all of these predictors to show that the world is not linear. If I just added stringency to the model and added all of the mobility variables to the model and the weather variables to the model, my model would be inflated with variance, like multicollinearity, and we wouldn't get the full picture like we wanted. We wanted to build on top of the previous literature, not just confirm it. So, result number 1. So what you see here is a visualization of how I've plotted an interaction. The y variable is the variable, the dependent variable of the model. That's incidence, per 100,000 capita. And the x variable shows low residential mobility, mean residential mobility, and high residential mobility. And the 3 colors show low stringency, mean stringency, and high stringency. So let's take a look at the blue line. When we have high stringency, which the blue line suggests, and we have low residential mobility, that means people are supposed to stay at home, but they're not staying at home. We have higher cases or more cases of COVID-19, and the opposite is true when people are staying at home. If the stringency level is very low, the model does not predict that that COVID-19 incidence will fluctuate dependent on residential mobility. Yeah. So this is just a line from the paper. When restrictions were strong, we found increased residential mobility resulted in decreased COVID-19 incidence. And so our suggestion is that residential mobility can be used as a proxy to study social compliance. Yeah. So it needs to be in this interaction with stringency for this to actually work. Yeah, so I've only chosen 2 visualizations of interactions, and this is the next one. So I've swapped out residential mobility on the x-axis with 3 levels of temperature. So we can see that when there's not a lot of stringency implemented by the government, and we have low temperatures, COVID-19 incidents are expected to be high, while the opposite is true when temperature is high. So this confirms the point from the start. High temperatures reduce COVID-19 incidence. More residential mobility reduces COVID-19 incidence in general, so this is an average. This is not the interactions. And mobility around transportation hubs increase COVID-19 incidence. Traveling more incidence. Living closer in municipalities increases COVID-19 incidence. So about open source code and everything, you can take everything from here, all of the data sets, all I've made. You could go to my GitHub, I have everything in there. Yeah. That's all for me.
Questions for Lasse? Just one. One here.
And thank you, Lasse. It was very interesting to listen to your talk. So just to understand the temperature correctly, is your hypothesis that that coronavirus will die in warmer or disintegrate in warmer waters and therefore not spread?
No, our hypothesis was not that specific because we looked at the average societal incidence over time. So it didn't really matter whether we hypothesized that because the weather was warmer, people would stay inside, or people would go outside, and therefore they would not transmit as much COVID-19. So we wouldn't actually be able to tell from this study whether it's because of virus prevalence or because of changed social mobility, if that makes sense.
Yeah, it makes sense. You just cited, it looked like the title was like if it's in the bathing water or something, but
oh, no.
Thank you.